Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on microwave engineering. For this video, I'm going to concentrate on skin effect. Firstly, I will define what is skin effect and I'm going to explain why skin effect only affect at high frequency. Okay, so basically this will be the objective of this video. This video, okay, I will also explain why at high frequency, electricity only flow on the surface of the conductor, but they will avoid the center of the wire at all costs. So basically, this is actually the result of skin effect. There are various RF and microwave components. Okay, so this video, I will kickstart by discussing on wire, okay, which has the skin effect. Okay, so other than wire, we also have inductor and also capacitor. Okay, so this will be later on series discussion on microwave engineering. Guys, if you're keen to know more about microwave engineering, okay, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on microwave engineering. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Before I continue, okay, I'd like to urge you guys to help this channel by pressing the like button. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's quickly kickstart by understand what is actually a wire, okay, which I believe most of you guys have some idea what is actually a wire. Okay, a wire, okay, so basically we have two types of wire. One is the flexible strand, and we have this rod of metal. Okay, so this diagram here shows the rod of metal. They are more solid, while this flexible strand is shown over here. Okay, so they are actually more flexible. Okay, so for wire, most of the time, they are made up of good conductor. For example, copper and also aluminum. Okay, so these two materials are considered a good conductor. So the key purpose of wire is to conduct electricity in electrical and electronic system. Wire, most of the time, they require it to be insulated. Okay, so from this picture, you can see that they are actually insulated with rubber. Okay, so basically, you can see the color here. They are actually insulated with rubber so that we will not accidentally touch the wire and get electric shock. Some of the extreme time, then we will have this so-called exposed wire, but I will say that it's very rare. Some example of a wire, we have this live wire. Okay, so typically it's red in color. They carry current in a circuit. We also have the ground wire, which is a safety conductor. Okay, they are mainly either yellow or blue color. So as I mentioned earlier on, this actually prevent us to have electric shock. So they basically shunt all the current into the ground. We need to discuss quickly on the wire size, okay, because this actually has some impact on the skin effect. So let me quickly discuss on the wire size. Okay, this wire size is so-called standardized by this American wire gauge, AWG. Okay, the AWG number, okay, is inverse proportional to the wire's diameter. Okay, so which means that the smaller the number, the bigger the wire diameter. The bigger the number of AWG, the smaller the wire diameter. Okay, let's take a look on the next page, okay, which is the AWG charge. Okay, so basically this diagram here shows the AWG charge. Okay, so basically on your left, these are all the AWG number. Okay, so basically you can see that AWG number start to increase when we actually move down. Okay, on your right, okay, you have this diameter. Okay, so let's just focus on this bare diameter. Let's just neglect this for a moment. Okay, so basically the bare diameter, you can see again from here, when AWG actually increase, okay, you can see that the size of the cable actually reduce. Can see over here? So basically, this is a relationship which I have explained on my previous slide. When AWG actually increase, the size of the diameter actually reduce. Another important criteria, which is the resistance. Okay, so basically from here you can see that when the size of the diameter reduce, okay, you can see that the resistance actually increase. Okay, so this makes sense, right? Imagine, okay, you have a bigger so-called wire with a bigger diameter. So basically, with a bigger diameter, current can be easily flow. So therefore, you expect the resistance to be small. However, when you actually move further down, you can see that the diameter of the wire start to reduce, which means that the wire is getting thinner and thinner. And again, you can foresee that the resistance also start to increase. Okay, so basically in this table here shows three relationships. First is AWG. Second is the diameter of the wire. Third will be the resistance of the wire. Okay, so basically on my next video, we have some form of calculation in order to fully understand how to find the resistance of the wire. Okay, so let's quickly discuss on the equivalent circuit of a wire. Okay, so again, I will break the discussion into 2 points. Okay, at low frequency, okay, the equivalent circuit of a wire is just the resistor. However, okay, at high frequency, okay, typically we have an equivalent circuit of a series inductor together with a series resistor, as you can see from here. Okay, so later on I will explain, okay, on this equivalent circuit here. So in some of the case here, we may have some capacitive effect, but in the interest of this, we make the circuit much more easier to understand. Okay, so I have omit away the capacitive effect. Okay, so this is also quite negligible. Okay, let's come to the equivalent circuit of the wire over here. Okay, as I mentioned earlier on, we discussed this under two frequency. One is under low frequency. Okay, so what happened here is basically from here you can see that the resistor will be so-called consistent irregardless of the frequency. So basically, if we have a good conductor, the R will be very small. Okay, let's study on the inductor. Okay, so the reactance of the inductor will be 2 pi FL. For this case here, because the frequency is small, so you're going to have a small frequency, and the overall reactance of this inductor will be very, very small. And so therefore, okay, for low frequency, I actually can omit away the inductor. Therefore, as I mentioned earlier on, for low frequency, the equivalent circuit of a wire is just the resistor. So basically, this is the reason. However, things change differently under the high frequency. Okay, again, they will have still a small resistor. As I mentioned, resistor actually is so-called independent from frequency. The resistor value actually depend on the conductivity of the wire. So if we use a good conductor, okay, the R will be still remain very small. However, for this case here, you can see that the reactance of the inductor actually will be drastic different because the frequency now will be a significant number because under high frequency. So therefore, this reactance of the inductor can be quite significant big, and we cannot omit this. So in short, over here, you can imagine that at low frequency, okay, so the equivalent circuit of a wire is just a very small R, which is the loss of the conductor. However, at high frequency, we still need to consider the inductor, which makes the equivalent circuit of wire not that short circuit anymore. As you can see that they have both the effect of resistor and also inductor. Okay, let's come to these two, okay, while I explain fully on the equivalent circuit of a wire. Okay, so the R, which I mentioned earlier on, they actually represent the loss of energy as current flow through the wire. Okay, this is actually due to the wire material property. In short, there is no perfect conductor. Perfect conductor means that there will be 0 ohm. Okay, so because in this radical world, okay, we still have some form of loss, even is a good conductor. So this R actually account for the loss of the conductor of the wire. As for inductor, okay, so this actually represents the wire ability to resist change in current flow. Okay, so in short, this inductor will have some significant impact on the skin effect, which we are going to discuss later on. Okay, so as I mentioned that this will be especially true at higher frequency. When frequency start to increase, this may affect the performance of the wire. Okay, it may not be short circuit anymore. So therefore, we need to consider this at a very high frequency. Okay, let's come to the skin effect. Okay, so before I come into the definition of skin effect, okay, let me quickly describe, okay, so this tree diagram here. So we have three type of scenario. Okay, first is under DC current, which means that frequency is almost at 0 hertz here. So you can see that, okay, for DC current, the current flow evenly at the cross-section view of the wire, as you can see from here. So they flow evenly. So now, under increased frequency, okay, under the category of low frequency in the AC condition, okay, you can see that the current will avoid the center of the conductor. They will mainly flow in this so-called orange region here. So this is with low frequency at this moment. So from here, you can see that when the frequency is further increased, okay, you can see that the current reluctant to flow at the center of the conductor, okay, due to the magnetic field generate, which I will explain on the next slides. You can see that the cross-section area for the current to flow is even smaller now. So basically, this is the effect, okay, under almost 0 hertz, when we actually increase the frequency slightly, still consider under low frequency, and we further increase the frequency to high frequency, this is actually the effect of skin effect. We classify this. So I want to highlight this. Okay, so skin effect is actually in this orange zone. So basically, you can see that this is actually the skin effect. So when we actually increase the frequency, you can see that skin depth basically becomes smaller. Okay, so basically, this is the effect of skin effect at high frequency. Let's understand the definition of skin effect. Okay, so skin effect is the tendency of an AC to distribute itself within a conductor such that the current density is highest near the surface and decrease exponentially with depth. Okay, so basically this is what I mean. So most of the time, okay, under the skin effect here, you can see from here, you can see that this actually has a so-called high current density, probably the highest current density, and they will actually reduce exponential if we go to more so-called depth into the center of the core of the wire. Okay, so this phenomenon actually occurs due to opposing eddy currents induced by the changing magnetic field generated by the AC. Okay, so on my next slide, I will show you this. As a result, most of the current flow near the conductor's surface because the outer layer and a depth known as the skin depth. Okay, so this is actually the quick definition of skin effect at high frequency for wire. Okay, so let's take a look on this slides here to understand fully, okay, the skin effect. Okay, so again will be under two type of scenario. One is under low frequency, another one will be under high frequency. Okay, as I mentioned early on, at low frequency, okay, all the charge carrier, they are evenly distributed across the cross-section view of a wire, as you can see from here, which means that almost 0 hertz. Okay, so that you can see that the current actually evenly distribute, okay, across the cross-section view of the wire. However, when the frequency start to increase, okay, there will be an increase of magnetic field at the center of the conductor. Okay, so basically this is what I mean. Okay, so when we actually increase the frequency, okay, so there will be an increase of magnetic field at the center of the conductor. This actually present an impedance to the charge carrier. Okay, so there will be some impedance over the center of the conductor. So this actually prevent the current to flow at the center of the conductor, okay, because of the magnetic field. Okay, so this will increase the current density around the edge of the conductor, which is known as skin effect. Okay, keep this in mind. When I actually increase the frequency, you can imagine that this dotted circle become bigger and bigger. Okay, so I'm going to have a more drastic skin effect, okay, when we actually increase the frequency. Okay, so basically this is actually the quick discussion on the skin effect. Okay, so as the frequency is increased, the current will move to the surface of the wire. Okay, this will cause higher conductor losses and field radiation. Okay, so to overcome this problem, okay, we need to have a shield wire or a few confined lines are used at high frequency. Okay, so basically, let's study this tree diagram here. So this is for low frequency. As I mentioned that under DC, the current density is almost evenly distributed at the cross-section view of the wire. When we actually increase the frequency, okay, you can see that they actually want to travel at the surface of the conductor. And if we further increase the frequency, okay, they will be even nearer to the edge of the conductor. And this potentially become a radiate field. So basically, instead of traveling along the conductor, you have some form of energy that is actually released up. Okay, so this can be undesired. So therefore, we actually have a shield wire to contain this radiate field. One example will be the coaxial cable. As you can see from here, this is actually so-called the conductor, okay, the wire, if you want to say this, but typically it's not that. We call this a wire, but over here, you just imagine it's a conductor, okay, which is shown over here. So you can see that we have some form of shield, okay. So this can be a ground, this can be a form of shielding. Okay, so basically this is one example, okay, why we cannot use wire at high frequency. We probably need to use coaxial cable to carry the high frequency signal. Okay, so hopefully you have some idea on this here. Guys, before I continue, okay, I need to seek your help, okay, for you to help me to press the like button. When more you guys actually help to press the like button, this video will have a better chances to reach out to a larger audience. So guys, help me press the like button now. Guys, urge you, if you have learned something from this channel, okay, so urge you to help me and support me by subscribe to this channel. Once again, thank you so much for your strong support. Let me continue the discussion. Again, let me quickly define what is skin depth. Okay, the depth into the conductor at which the charge current density fall under 1 over E, okay, which is the exponential or 37% of its value along the surface is known as skin depth. Okay, so let's not dwell so much on this here. Okay, I will explain this. Okay, so this means that 63% of the current flow in the surface at or above the skin depth. Okay, let's take a look on this diagram here. So what does this mean? Okay, which means that, okay, what is actually a skin depth? Okay, which means that 63% of the current actually flow in this shaded region. So we call this skin depth, which means that 63% of the current actually flow in this shaded region. We call this skin depth. Okay, which means that 37% actually flow above this region here. Then we know this as a skin depth. So from here, okay, earlier on, I have discussed that skin depth is actually a function of frequency and also the permeability of the medium and also the conductivity of the medium, which we are going to take a close look, the formula to calculate skin depth. But before I continue here, let's quickly understand how to obtain the skin depth area here. Okay, so the skin depth area will be the shaded region. How to get the shaded region here? I need to know the area of the bigger circle. And if I know the area of the smaller circle, I take the area of a bigger circle minus the area of the smaller circle, then I will have the area of the skin depth. So this is actually how I can actually calculate the skin depth area, as you can see from the equation over here. Okay, like I mentioned, my next video, I will have some form of calculation to calculate the skin depth. But at this moment, I hope you understand what is actually skin depth. Let me come to the equation for the calculation of skin depth. So this is the formula to calculate skin depth. Okay, so basically skin depth is actually represented by this symbol over here. You can see that they are actually a function of frequency. Okay, this W is actually equals to 2 pi f. They are also a function of the permeability of the material. They are also so-called a function of the conductivity of the material. Okay, so basically in short, I will do the so-called calculation example on my next video. But this in short is simply to show you the calculation of the skin depth. Okay, so there are different material and you can see that different material, they actually have the different conductivity. Okay, the conductivity actually will tell us how good, okay, the conductor of the so-called material. For example, silver has the best conductivity, okay, which means that the resistor value will be the smallest if we use silver. But I guess you know that none of us are going to make wire made of silver. It will be very costly, okay, although it has the best conductivity, but it will be very costly if we have wire made of silver. So the next best option will be copper. As you can see from here, the copper actually always will be the reference one because most of the time, most of the wire we actually use copper to meet the wire. So from here you can see that the relative conductivity of wire, which is the reference number, which is 1. The permeability, okay, as long as if it's a metal, okay, I believe that the permeabilities of the material will be almost equals to 1, as you can see from here. Okay, so on my next video, I will have some form of calculation. Okay, but at this moment, okay, I just want to share the formula of the skin depth. From here, you can see that if my frequency increase, my skin depth actually reduce. Okay, because when I actually reduce the skin depth, which means that this is actually a skin depth, I'm going to have more severe issue. When my frequency increase, my skin depth becomes smaller, which means that it will be looking at this condition. When my frequency is so-called low, this thing is still so-called bigger than earlier on, so I will have this form as a skin depth. So basically, in short, from here, you can see that the higher the frequency, okay, I'm going to have this kind of situation rather than this. Okay, so this is a quick definition on skin depth. Let's move on. Okay, so let's discuss the factors that will influence the skin factor. Okay, come to the current. Okay, I always mention that for skin depth, we always break into high frequency and low frequency. I have discussed this. Okay, let's do a quick one on this here. At low frequency, the skin effect is negligible and current distribute uniformly across the conductor. However, at high frequency, the effect becomes significant. Okay, so basically they confine the current to the conductor surface, which I have discussed. Okay, let's come to the conductor material. Highly conductivity material are less affected by the skin effect than those with lower conductivity. Okay, one thing I want to highlight here. Okay, I hope you still remember. Okay, the skin effect is actually represent, or the wire is actually represent a resistor together with an inductor. If the conductivity is bad, the R will become a very big number and you may have some issue on skin effect. So therefore, okay, when we actually want to use a good conductivity material, we actually reduce the R value, which means that a wire is a perfect short circuit. Okay, so keep this in mind. Magnetic material actually exhibit a more pronounced skin effect. So basically, if we use magnetic material, you may have drastic skin effect as compared to the metal material. Coming to the size and shape of the conductor, large conductors actually have a larger so-called cross-section area. Okay, so basically this actually increase the potential for the skin effect. Hollow, okay, or strain conductor, okay, can mitigate the effect by providing a larger effective surface area. Okay, so basically over here you can see that if we need to use wire, then we probably want to use those flexible so-called strain conductor rather than the rod of metal. Okay, so basically this is what you want to say. As for temperature, okay, when we actually increase the temperature, okay, you actually increase the resistance value also. So which indirectly also increase the skin depth. So basically, these are all the factors that will affect the skin effect. Okay, current, as I explained earlier on, how they flow or so-called on the wire at low and also high frequency. Coming to the conductor, okay, so the conductor actually will affect the R value. Okay, so therefore we want to keep the R to be as small as possible so that we are going to have a attractive so-called losses, okay, rather than to have a big losses. Size and shape of the conductor. So in short, over here you can see that okay, we want to make a hollow because current don't like to flow at the center of the wire. So why not make a hollow conductor or a strain conductor so as to mitigate the effect here? We also want to avoid the temperature, okay, because the higher the temperature, the higher the resistor value, which indirectly also will have some effect on the skin depth here. Okay, coming to my last slide. So what are the methods that we actually can do to reduce the skin effect? Okay, so this is what I mentioned earlier on. We can use strain or hollow conductor. Okay, so this design actually distribute current over a larger surface area and they actually minimize the skin effect. Coming to the material selection here, okay, high conductivity material like copper or aluminum actually reduce the resistive loss, okay, which is caused by the skin effect. Again, this is something that I've already touched on. Okay, frequency management, okay, if possible, okay, we always want to lower the operational frequency in a power system. Okay, so this will also decrease the skin effect impact. Coming to the one that I have not really discussed is on the surface coating and treatment. Okay, we have some special conductivity coating, okay, or treatment that can actually enhance the surface conductivity. Hence, this will mitigate the skin effect. Okay, so from this slide here, you can see that there are actually 4 methods to reduce the skin effect. Okay, with this, I like to end my discussion. Okay, again, urge you to help this channel by like this video and also subscribe to this channel. Once again, thank you so much for your time. Thank you so much, and I hope to see you guys soon. Bye for now. Thank you.